Imagine that you have come to a concert. If it is a classical music concert, each seat is occupied by only one person. Two people cannot sit on the same chair. And now imagine an open-air rock festival. At one point of the lawn there can be as many people as you want that can stand on top of each other, lie in a heap. This is how the two main categories of particles in our universe behave. All particles are divided into fermions and bosons. And this is not just a classification for the convenience of physicists. It is a fundamental difference that determines the entire structure of matter. Fermions are particles with a spin equal to half of an integer. 1 second, 3 seconds, and so on. These include electrons, protons, neutrons, quarks. That is everything that ordinary matter consists of. Bosons have an integer spin 0, 1, 2. These are photons of light, gluons, W and Z bosons, and the Higgs boson. The key difference between the two is described by the Pauli Exclusion Principle, which only works for fermions. This principle states that two identical fermions cannot be in the same quantum state at the same time. What is a quantum state? This is the complete set of characteristics of a particle. Its energy, momentum, spin, position in space. If two electrons are in an atom, they cannot have an absolutely identical set of all these parameters. Why is this so important? Imagine that the Pauli principle does not exist. Then all the electrons in the atom could fall to the lowest energy level, closest to the nucleus. All the atoms would collapse into tiny, dense clumps. Chemistry would cease to exist because it is the distribution of electrons in different orbitals that creates chemical bonds. There would be no molecules, there would be no life, there would be no you reading this text. Let's look at a specific example. Take a helium atom with 2 electrons. Both electrons can be in the first orbital closest to the nucleus, but only if their spins are directed in opposite directions, one up and the other down. This makes their quantum states different. If we were to try to add a third electron to this orbital, it would be impossible. All the combinations are busy. The third electron is forced to move to the next energy level, further away from the nucleus. That is why the periodic table of Mendeleev has its own structure. Electrons fill the atomic orbitals layer by layer, obeying the Pauli principle. And what about bosons? They behave completely differently. Any number of bosons can be in the same quantum state. Moreover, bosons even prefer to do so. This is called Bose condensation. The most famous example is a laser beam. In a laser, billions of photons, which are bosons, are in exactly the same state. They have the same frequency, phase, direction of motion. That is why the laser beam is so narrow and powerful. Where does this difference come from? It's about quantum statistics and the properties of the wave function. When you swap two identical particles, the wave function of the system can either remain the same or change sign. For bosons, it remains the same. They don't care who is where. They are indistinguishable and happily crowd together. For fermions, the wave function changes sign, and if two particles try to occupy the same state, the wave function will turn to 0. Such a configuration simply cannot exist mathematically. This is related to the spin of particles through the theorem of the relationship between spin and statistics, which is one of the cornerstones of quantum field theory. Particles with half-integer spin always obey Fermi-Dirac statistics and are fermions. Particles with integer spin obey Bose-Einstein statistics and are bosons. This is not an accident or a convention. It is a profound consequence of the requirements of relativistic invariance and causality in quantum mechanics. Let's look at the practical consequences. The solidity of a substance, the table on which your computer stands, the floor under your feet, exists thanks to the Pauli principle. When you press on the table, the electron shells of the atoms in your hand try to get closer to the electron shells of the atoms in the table. But electrons cannot occupy the same states. There is a huge quantum pressure, which creates a feeling of solidity. In fact, atoms are almost completely empty, but the Pauli principle creates an impenetrable barrier. Another example is white dwarfs and neutron stars. When an ordinary star runs out of fuel, gravity begins to compress it. In a white dwarf, the compression is countered by the pressure of a degenerate electron gas. The electrons are so densely packed that the Pauli principle creates a quantum pressure that stops the collapse. In a neutron star, the matter is compressed even more, and now neutrons create this pressure. Without the Pauli principle, these objects would instantly collapse into black holes. Bosons, on the other hand, create completely different phenomena. The superfluidity of liquid helium at temperatures close to absolute zero occurs because helium, 4 atoms, which are bosons in general, change into a single quantum state to form a Bose condensate. The liquid begins to flow without friction, can rise along the walls of the vessel, flow through the smallest cracks. This is a macroscopic manifestation of quantum mechanics. Superconductivity works on a similar principle. At low temperatures, the electrons in the metal combine in pairs called Cooper pairs. Each pair behaves like a boson, although the individual electrons are fermions. These pairs condense into a single quantum state and can conduct electric current without resistance at all. Interestingly, the difference between fermions and bosons is evident even in cosmology. In the early universe, when it was incredibly hot and dense, matter and radiation were in thermodynamic equilibrium. As fermions and bosons expanded and cooled, they began to behave differently. The CMB radiation that we observe today are photons, bosons, which propagate freely from the moment of recombination. And the relic neutrinos, which are fermions, form their own background with different properties that in quantum field theory, each particle is described as an excitation of the corresponding field. An electron is an excitation of an electron field. A photon is an excitation of an electromagnetic field. And the operators who create and destroy these excitations are subject to different switching rules. For bosons, operators commutate in a certain way. For fermions, they commutate. This mathematical difference leads to all the physical consequences that we are talking about. Imagine 2 electrons moving through space. If you swap them, the total wave function of the system should be anisymmetric. It changes sign. This can be written mathematically. If the state with the first electron at point A and the second electron at point B is denoted as psi AB, then psi equals psi AB. Now imagine that A and B are the same point, the same state. Then psi A equals psi A. The only number that is equal to itself with the opposite sign is 0. Therefore, psi A equals 0, and such a state cannot exist. For bosons, the opposite is true. The wave function is symmetrical. Psi AB equals psi BA. And if A equals B, then psi A equals psi A. No contradictions. Moreover, the amplitude of the probability of finding many bosons in one state even increases with the growth of their number. If there are already n bosons in the state, the amplitude of adding another one is proportional to the root of n plus 1. This quantum amplification is what makes stimulated emission, on which the laser is based possible. Let's now think about how this affects the interaction of particles. Forces in nature are carried by bosons. The electromagnetic force is carried by photons, the strong nuclear force by gluons, and the weak force by W and Z bosons. Why bosons? Because bosons can be created and destroyed in any quantity. When two electrons repel each other, there is a constant exchange of virtual photons between them. These photons arise literally out of nothing, carry momentum and energy, and disappear. If force carriers were fermions, they could not be created so freely. The Pauli principle would interfere with this process. There is an interesting exception to the rule that forces carry bosons. Gravity in quantum theory should be carried by a hypothetical graviton, which should also be a boson with spin too. But gravity is still not fully quantized, and this is one of the greatest unsolved problems in physics. However, all theories predict that the graviton must be a boson. It is interesting to look at the statistics of particles at different temperatures. At very high temperatures, when the energy of the particles is much greater than the distance between the levels, the distinction between fermions and bosons is blurred. Both groups behave roughly like a classical ideal gas. Bosons condense to the lower energy level, forming a Bose condensate. Fermions are distributed over the levels, filling them from the bottom up. Each level can accommodate a limited number of particles. In metals, electrons form the so-called Fermi sea. At absolute zero, all energy levels are filled from below to a certain energy, which is called Fermi energy. Above this energy, all levels are empty. The boundary between filled and empty states is called the Fermi surface, and its shape determines many properties of the metal: electrical conductivity, thermal conductivity, magnetic properties. When you heat the metal, the electrons near the Fermi surface gain energy and move to higher levels. But most of the electrons deep below the Fermi surface stay in their places. They can't move to neighboring levels because they're already occupied. This explains why the heat capacity of metals is associated with electrons quite small. In classical physics, every electron would have to contribute to heat capacity, but Pauli's principle prohibits most electrons from absorbing energy because all nearby states are occupied. Only electrons near the Fermi surface can participate in thermal processes. Composite particles can be either fermions or bosons, depending on what they are made of. A proton is made up of 3 quarks, each of which has 1/2 spin. 3 halves can add up to 1/2, so a proton is a fermion. A helium, for atom, contains 2 protons, 2 neutrons, and 2 electrons, 6 fermions in total. 6 halves make an integer, so helium, 4, generally behaves like a boson. Helium-3, on the other hand, has only 1 neutron in its nucleus, which means only 5 fermions, and that makes helium-3 a fermion. And indeed, helium-3 does not become superfluid at the same temperatures as helium-4. It needs much lower temperatures at which atoms begin to form Cooper pairs. In modern condensed matter physics, scientists have learned how to create artificial systems where quantum statistics can be observed under controlled conditions. Using laser cooling, it is possible to cool a cloud of atoms to temperatures billionths of a degree above absolute zero. At these temperatures, the boson atoms form a Bose condensate. They all go into the same quantum state, and the cloud begins to behave like one giant quantum object. This makes it possible to study quantum phenomena at scales visible to the naked eye. Fermions are more difficult because they refuse to come together. but they have learned to cool them to incredibly low temperatures. In this case, a Fermi gas is formed, where Fermion atoms fill all available states to a certain energy. This made it possible to experimentally study the quantum pressure of degeneracy, which keeps white dwarfs from collapsing, but in miniature, in the laboratory. There is another surprising phenomenon. Quantum statistics affect chemical reactions. When two molecules collide and can react, quantum mechanics tells us that there is a certain amplitude of probability for each outcome. But if identical particles are involved in the reaction, for example, two identical atoms, it must be taken into account that these particles are indistinguishable. For Fermion atoms, the wave function must be antisymmetric. For bosons, it must be symmetrical. This changes the amplitudes of reactions and can make some reactions forbidden or, conversely, intensified. In astrophysics, the distinction between fermions and bosons determines the fate of stars. The star, while thermonuclear reactions are taking place in it, is kept from collapsing by the pressure of hot gas. When the fuel runs out, gravity begins to win. If the mass of the star is less than about 1.4 solar masses, this is the Chandrasekhar limit. It becomes a white dwarf where the pressure of degenerate electrons stops the contraction. If the mass is greater, electrons are pressed into protons, forming neutrons, and a neutron star is formed, where the pressure of degenerate neutrons holds matter together. If the mass is even greater, more than about 2 to 3 solar masses, even neutron pressure doesn't help, and a black hole forms. All these limits are determined by the Pauli principle for fermions that in quantum chromodynamics, the theory of the strong interaction. The Pauli principle plays a critical role in the structure of protons and neutrons. Inside a proton are 3 quarks. If there were no additional quantum characteristic, this would pose a problem. 3 quarks of the same type could not exist together because of the Pauli principle. Solving this puzzle led to the discovery of the color charge. Each quark carries one of 3 colors: red, green, or blue. These are not real colors, of course, but quantum numbers, but the name stuck. The 3 quarks in a proton have different colors, which makes them distinguishable and allows them to coexist. Gluons, the carriers of the strong interaction, carry a color charge themselves, unlike photons, which do not carry an electric charge. This makes the strong interaction incredibly complex. Gluons can interact with other gluons, creating nonlinear effects. There are 8 types of gluons, all of them bosons, and they can exist in any number in a single state. In particle physics, there's a remarkable symmetry between fermions and bosons, which is called supersymmetry. This hypothetical symmetry predicts that every fermion must have a boson partner, and vice versa. An electron must have a superpartner selectron, and a photon must have a photino. So far, none of these supersymmetric particles have been detected, despite intensive searches at the Large Hadron Collider. If supersymmetry exists, it must be broken at the energies available to us. Otherwise, we would have already seen these particles. It is interesting to think about what happens to fermions and bosons under extreme conditions. In the core of a neutron star, the density of matter reaches the density of the atomic nucleus or even exceeds it. Neutrons are packed so tightly that their wave functions overlap. Fermi energy becomes enormous. The most energetic neutrons move at speeds close to the speed of light. At even higher densities, exotic states of matter can appear. Hyperon stars, where strange quarks appear, or quark stars, where neutrons generally decay into their constituent quarks, forming quark matter. In the early universe, in the first microseconds after the Big Bang, the temperature was so high that quarks and gluons existed freely in the state of quark-gluon plasma. This state is recreated in modern experiments at heavy ion accelerators, when lead or gold nuclei collide at near-light speeds. At the moment of collision, a tiny drop of quark-gluon plasma appears for a fraction of a second, where quark fermions and gluon bosons move freely, not bound in protons and neutrons. The Pauli principle has a surprising consequence for information. Because two fermions cannot be in the same state, each fermion occupies a unique cell in phase space. This limits the amount of information that can be recorded in a given amount of space. There is no such limitation for bosons. In principle, you can pack as many bosons as you want into one state. This has to do with fundamental questions in quantum information theory and the holographic principle, which suggests that the maximum amount of information in a region of space is proportional to the area of the boundary of that region, rather than the volume. Quantum computers use quantum bits or qubits. They can be realized both with the help of fermions, for example, electron spins, and with the help of bosons, for example, polarization of photons. Each approach has its own advantages. Electron spins are stable and well isolated from their surroundings thanks to the Pauli principle, but they're difficult to manipulate. Photons are easy to control and transmit over long distances, but more difficult to store and make interact with each other. There is a whole class of quasiparticles, excitations in condensed matter that behave like particles but are not fundamental. Some of them have amazing statistical properties. In two-dimensional systems, at very low temperatures, and in strong magnetic fields, excitations with a fractional charge can occur, which are subject not to Fermi-Dirac statistics or Bose-Einstein statistics, but to the so-called anionic statistics. When you swap two anions, the wave function is multiplied by a complex phase factor that is neither +1 nor -1. This is possible only in two spatial dimensions and impossible in three-dimensional space. Anions are observed in the phenomenon of fractional quantum Hall effect. When electrons are confined to a two-dimensional layer and placed in a strong magnetic field, they form a correlated state where the elementary excitations carry a fractional charge, 1/3 or 1/5 of the electron's charge, and obey the anionic statistics. These exotic objects are seen as a potential basis for topological quantum computers that would be error-resistant due to the topological protection of quantum information. Let's return to ordinary fermions and bosons. Understanding their difference is critical for many modern technologies. Semiconductors work because electrons fill energy bands according to the Pauli principle. In pure silicon, at absolute zero, all states in the valence band are filled and the conduction band is empty. When you add impurities or heat a material, some electrons get enough energy to jump into the conduction band. At the same time, holes remain in the valence zone, unoccupied states that behave like positively charged particles. By controlling the concentration of electrons in holes, it is possible to create diodes, transistors, LEDs, the entire basis of modern electronics. In LEDs, electrons and holes recombine to emit photons. Electrons and holes are fermions, and a photon is a boson. This transformation of fermions into bosons is possible because energy and momentum are conserved, but the total number of particles of each type is not. Fermions can be born and destroyed if this happens in particle-antiparticle pairs. When an electron and a positron annihilate, they are converted into two photons. Two fermions yield two bosons. Neutrino astronomy uses the fact that neutrinos are fermions that almost do not interact with matter. They can fly through the entire Earth, practically not noticing it. Neutrino detectors are huge reservoirs of water or other liquid surrounded by thousands of ultra-sensitive photomultipliers. When a rare neutrino does interact with a nucleus in water, a charged particle is created that travels faster than the speed of light in water, which causes Cherenkov radiation, a faint flash of light that detectors detect. Fermions and bosons behave differently in a gravitational field. All particles fall with the same acceleration. This is the principle of equivalence, the foundation of general relativity. But quantum effects make subtle differences. Ultra-precise cold atom experiments study how fermions and bosons respond to gravity at the quantum level. So far, no differences have been found from the predictions of general relativity, but these experiments test the fundamental principles with unprecedented precision that in high-energy physics. Particle collisions at accelerators constantly produce new particles from pure energy. Here, the difference between fermions and bosons is manifested in the cross-sections of reactions, the probabilities of various processes. The production of a fermion-antifermion pair has one cross-section. The production of bosons has another. Physicists calculate these sections using Feynman diagrams, where each line represents a particle and each vertex represents an interaction. For fermions, arrows on lines are used. For bosons, wavy or dotted lines without arrows. Interestingly, some exotic theories predict the existence of particles with completely unusual statistics. In string theory, where particles are represented as vibrations of tiny, one-dimensional objects, there may be states that do not fit into the usual fermion-boson classification. But at the low energies available to our experiments, all these exotic effects are hidden, and we only see ordinary fermions and bosons. In the cosmology of the inflationary expansion of the universe, a key role is played by the hypothetical scalar field of the inflaton, whose quantum should be a boson with spin 0. This field in the early universe was in a high-energy state and was slowly sliding into a minimum potential, causing an exponential expansion of space. Quantum fluctuations in this boson field gave rise to tiny density inhomogeneities, which then grew into the galaxies and clusters of galaxies we see today. Dark matter, which makes up about 85% of all matter in the universe, may be made up of either fermions or bosons. We don't know yet. If they are fermions, such as hypothetical particles of the neutralino type, they must obey the Pauli principle, which limits their density at the centers of galaxies. If they're bosons, such as axions, they can form a Bose condensate with a very high density. Observations of the distribution of dark matter in dwarf galaxies attempt to distinguish between these scenarios. The Higgs mechanism, for which the Nobel Prize was awarded in 2013, explains why fermions and some bosons have mass. The Higgs field permeates the entire universe, and particles acquire mass through interaction with this field. The Higgs field itself is a scalar boson field, and its quantum, the Higgs boson, was discovered at the Large Hadron Collider. Different particles interact with the Higgs field with different strengths. So the top quark is very heavy, and the electron is light, and the photon does not interact at all and remains massless. In biology, quantum effects related to particle statistics can play a role in some processes. For example, in photosynthesis, The energy of light is carried by excitons, which are bonded pairs of electrons and holes that are bosons. These excitons can exhibit quantum coherence and carry energy with surprising efficiency through protein complexes. There are hypotheses that quantum coherence plays a role in birds' sense of smell, magnetoreception, and even brain function, although these ideas remain controversial. In plasma physics, the difference between fermions and bosons affects the collective behavior of charged particles. In plasmas, Fermi electrons create degenerate pressure at high densities, which is important in objects such as white dwarfs. Photon bosons of radiation can be in thermodynamic equilibrium with the plasma, forming what is called blackbody radiation. In fusion reactors, where they try to reproduce the processes that take place in stars, it is necessary to keep the plasma at temperatures of hundreds of millions of degrees, at which the quantum effects of particle statistics become important. Spin systems in condensed matter demonstrate a wealth of quantum phenomena. In ferromagnets, the spins of electrons line up in parallel due to the exchange interaction, which follows directly from the Pauli principle and the wave function antisymmetry for fermions. Elementary excitations in magnets. Magnons are bosons, quanta of spin waves. At low temperatures, magnons can form a Bose condensate, which leads to interesting magnetic phenomena. In quantum optics, the distinction between fermionic and bosonic states of light is particularly clear. The normal light of a light bulb is made up of incoherent photons in different states. Laser light is a coherent state where a huge number of photons are in a single quantum state. There are also non-classical states of light, such as compressed states or states with a certain number of photons, which are used in quantum technologies. Photon bosons are easy to create and detect, making them ideal carriers of quantum information for quantum communication. In topological insulators, materials that are insulators on the inside but conductors on the surface, electrons on the surface behave in a very unusual way. Their spin is tightly coupled to the direction of motion, and they're protected from scattering by impurities by the topological properties of the system. This is a direct consequence of the Pauli principle and the specific structure of electronic states. Topological insulators can become the basis for spintronics. Electronics where information is encoded in the spin of an electron and not only in its charge. In the astrophysics of jets, powerful ejections of matter from the vicinity of black holes and neutron stars, the interaction between fermionic matter and boson radiation fields creates complex dynamics. Charged particles fermions are accelerated in magnetic fields and emit photon bosons through a synchrotron mechanism. These photons can have enormous energies, reaching the gamma-ray range. Observations of jets help to understand the physics of extreme states of matter and radiation. In quantum measurement theory, the process of measuring a quantum system fundamentally depends on whether we measure a fermion or a boson. When you measure the state of a photon, you usually absorb it. The photon disappears during the detection process. This is normal for a boson. But when you measure an electron, it continues to exist after the measurement, just its state changes. Non-destructive measurements are possible for both types of particles, but they are implemented in different ways. In the physics of ultra-cold atoms, they have learned to create optical lattices, periodic structures of standing light waves that act on atoms like a crystal lattice. In such a lattice, you can place either boson atoms or fermionic atoms and study their behavior. Bosons easily form a superfluid state, flowing through the lattice without friction. Fermions form an analog of a metal or an insulator, depending on the parameters. These systems allow you to simulate the behavior of electrons in solids, but under much more controlled conditions in quantum electrodynamics. The most precisely verified theory in physics, the interaction between Fermi electrons and boson photons, is described with incredible accuracy. The anomalous magnetic moment of the electron has been calculated and measured to the 12th decimal place, and a theory and experiment agree perfectly. These calculations include Feynman diagrams of all orders, where virtual photons are constantly being produced and disappearing around the electron, and virtual electron-positron pairs appear and annihilate in a vacuum. A vacuum in quantum field theory is not a void, but a boiling sea of virtual particles. The Heisenberg uncertainty principle allows for short periods of time to disrupt the conservation of energy, during which time particle-antiparticle pairs can occur. For fermions, these are always pairs, electron-positron, quark-antiquark, because quantum numbers like electric charge and lepton number must be conserved. For bosons, there are fewer such restrictions. Photons can be born one by one from the curvature of the electromagnetic field. The Casimir effect is a direct manifestation of quantum fluctuations in the vacuum. If two uncharged metal plates are placed very close to each other in a vacuum, there is an attraction between them. This is because the metal plates limit the spectrum of virtual photons that can exist between them. Only certain wavelengths are allowed. There are no restrictions on the outside of the wafers, and the pressure of virtual photons is greater there, which creates a resultant force that presses the wafers together. The effect was measured and exactly matches the predictions of quantum theory. In neutron stars, under certain conditions, pion or kaon condensates can occur. Pions and kaons are mesons, composite particles of quark and antiquark that are bosons. At high densities, it is energetically advantageous for a large number of these bosons to enter a single state with zero momentum, forming a condensate. This changes the equation of state of a neutron star and affects its maximum mass and radius. In hadron physics, particles involved in the strong interaction. The combination of quarks determines whether the resulting particle will be a fermion or a boson. Mesons are made up of a quark and an antiquark, with only two fermions, so mesons are bosons. Baryons are made up of three quarks, an odd number of fermions, so baryons are fermions. There are exotic hadrons, tetraquarks of 4 quarks and pentaquarks of 5, whose discovery in recent years has confirmed that quarks can form more complex combinations than just ordinary mesons and baryons. In nuclear physics, the Pauli principle explains the magic numbers of nucleons. Nuclei with a certain number of protons or neutrons, 2, 8, 20, 28, 50, 82, 126, are particularly stable. This is because these numbers correspond to the fully filled shells in the nucleus, similar to the filled electron shells in the atoms of noble gases. When the shell is filled, the next nucleon must move to a higher energy level, which requires additional energy and makes the nucleus more stable. Beta decay, the process by which a neutron is converted into a proton, electron, and antineutrino, demonstrates the inner conversion of fermions. All participants in this reaction are fermions with spin 1/2. Inside the neutron, one of the down quarks turns into an up quark, emitting a W boson, which then decays into an electron and an antineutrino. This process is driven by the weak force, and its speed is determined by the weak force constant. In quantum chromodynamics at low energies, the phenomenon of confinement occurs. Quarks and gluons cannot exist in a free state. They're always locked inside hadrons. This is because the strong force, unlike the electromagnetic force, becomes stronger over long distances. Gluon bosons themselves carry a color charge and interact with each other to form color strings between quarks. When you try to separate two quarks, the energy of the string increases, and eventually it becomes enough to create a new quark-antiquark pair from a vacuum. In cosmic rays, streams of high-energy particles bombarding the Earth from space. Both fermions and bosons are present. Most cosmic rays are protons and fermions, but there are also nuclei of heavier elements and a small fraction of photons and neutrinos. When an ultra-high-energy cosmic ray hits the upper atmosphere, it creates a shower of secondary particles, a hadron cascade, where hundreds of thousands of particles of both types are born. The study of these showers helps to understand the physics of interactions at energies unattainable at terrestrial accelerators. In the theory of electroweak interaction, which combines electromagnetic and weak forces, the distinction between the photon and the W and Z bosons is blurred at high energies. All four gauge bosons, the photon, W+, W-, and Z0, become parts of a single electroweak field. But at low energies, thanks to the Higgs mechanism, the three bosons acquire mass and turn into carriers of the weak interaction, while the photon remains massless. This spontaneous symmetry breaking is one of the key mechanisms in particle physics. In two-dimensional materials like graphene, electrons behave unusually. Graphene is a single layer of carbon atoms that form a hexagonal lattice. Electrons in graphene are described by the Dirac equation for massless particles, even though the electron itself has mass. In the context of motion on graphene, the effective mass is 0. These electrons move at about 300 times the speed of light, and their behavior resembles that of relativistic particles. Under certain conditions, an analog of the quantum Hall effect can arise in graphene, where conductivity is quantized in an unusual way. In high-energy physics, there are electron and positron annihilation processes, where two fermions are converted into pure energy, which is then materialized into other particles. At low energies, photons are usually produced. At higher energies, muon antimuon, tau anti-tau, quark-antiquark pairs can be produced. The cross-section of these processes depends on what particles are produced, and measurements of these cross-sections at LEP-type colliders help to accurately determine the parameters of the standard model. In neutrino physics, there's an amazing phenomenon of neutrino oscillations. Neutrinos exist in three flavors: electron, muon, and tau neutrinos, but these states do not coincide with states of a specific mass. When a neutrino propagates through space, its flavor oscillates. An electron neutrino can turn into a muon and vice versa. This is possible only if neutrinos have mass, which has been proven in experiments to observe solar and atmospheric neutrinos. Neutrinos are fermions, and their mass arises through a different mechanism than the Higgs mechanism for charged leptons and quarks. In condensed matter physics, there are materials with strong electron correlations, where the interaction between Fermi electrons is so strong that the simple picture of independent particles ceases to work. Exotic states arise in these systems, such as high-temperature superconductivity, heavy fermions, where the effective mass of an electron is hundreds of times greater than usual, spin fluids, where magnetic moments remain disordered even at absolute zero temperature. All these phenomena are a direct consequence of the Pauli principle and the quantum nature of electrons. In future collider experiments, physicists hope to discover new particles beyond the Standard Model. These could be supersymmetric partners of known particles, additional dimensions of space-time, new gauge bosons, or dark matter. Each new discovery will require an understanding of whether the new particle is a fermion or a boson. That's the first question to answer because it defines all the other properties. In quantum gravity, a theory that is supposed to unify quantum mechanics and general relativity, the distinction between fermions and bosons persists. In the theory of loop quantum gravity, space-time is made up of discrete quanta, while in string theory, particles are different modes of string vibrations. But in both theories, particles are still divided into fermions and bosons, obeying the corresponding statistics. The Pauli prohibition principle and the distinction between fermions and bosons are not just a technical detail of quantum mechanics. This is a fundamental law of nature that determines the structure of matter on all scales, from subatomic particles to stars and galaxies. Without this principle, atoms would collapse into a point, stars would instantly turn into black holes, and there would be no chemistry, life, and consciousness. The fact that you can read this text, that there's a complex structure of matter, that the world is diverse and interesting. All this is a direct consequence of the fact that two identical fermions cannot be in the same quantum state. Understanding this difference reveals the beauty of the quantum world, where particles obey laws that are completely different from our everyday experience, yet precise, mathematically rigorous, and experimentally verified with incredible precision. Every electron in your body knows of the existence of all the other electrons through the Pauli principle. Every photon of light is free to attach to the laser beam because it is a boson. This is not a metaphor. It is a literal description of reality at the quantum level, the reality from which our entire world is built.